talk for a bit about vectors in the wild, so to speak, some actual concrete examples of nuts and bolts ways that we're representing real data that matters in the wild with vectors. Because one of my goals for this entire All the Math volume is to make this linear algebra stuff very concrete and real for you. It's easy to just think of matrices and vectors as just these boxes of numbers that you sort of manipulate in different ways, and a lot of times when you learn it that way, you're like, what's the point, right? I mean, this is math, and this is sort of an advanced math class, and it's taking things in a different dimension from what I learned before, but I still don't really get why you would ever do any of this stuff. And I want to make very clear that linear algebra is extremely applied and extremely valuable in a lot of applications that you're familiar with every day. So let me give you some examples with that, right? So one, as I mentioned briefly, is the notion of a time series. Right? I mentioned the stock price thing. You could also imagine something like temperatures, right? Let's say I want to figure out, what has the temperature been like in my area over time. So maybe it looks something like this, and it's got like a little peak for the middle of every day. And then we had sort of a hot spell here, right? If you look at the weather over time, this is likely what you'll see in a region. And that's because there's sort of a peak every day at noon-ish, and that's because that's when the sun is the highest and it's heated up the earth and stuff. It might happen a little bit afternoon now that I think about it. But each one of these is like, noon on Monday, noon on Tuesday, noon on Wednesday, etc. And down here is like, midnight, so that's 12 a.m., p.m., and here's 12 a.m., and here's 12 p.m., and here's 12 a.m., etc., right? So there's sort of a cyclical nature to it. And then here, maybe we sort of had a hot spell, and wow, it got up to 90 degrees or something like on this day here, or maybe even a little bit over, right? So this whole thing is effectively a vector quantity, because what we could do is sample the temperature outside every hour or something like that, and we'd make a great big vector, right? It was 72, then the next hour it was 72, then it was 73, then it was 74, then it was 78, then it was 82, and then after a while it went back down to 81 and 74, right? So imagine some big vector that represents that, and we could use this in some numerical algorithms to help us predict the weather. We could say, based on past performance, when we saw it going according to a certain pattern, what is it likely to be out here where the weatherman needs to actually make some predictions about this? So time series are a very, very common thing that are used for vectors. Another thing that's used is items with attributes. So I mentioned some examples of that before. Let me give you another one. Suppose I'm giving loans to somebody, right? And I want to say, is this person going to default on their loan if I give it to them? And maybe I want to collect some information about them. I want to say, well, I need to know their age. I need to know their credit rating. I need to know what the loan amount they've requested is. Loan amount. I need to know, what their salary is, so whether they can pay it back. Maybe there's some other things here. This is tailor-made for a vector representation here, because I'm going to say this person was 32 years old, and their credit score is 492, and they want to borrow, they're buying a house, and so they want to borrow, $300,000, and their salary right now is, $81,000 or whatever it is. And basically the reason to treat these as a vector is because these things all go together, right? Each one is individually a scalar, yet they're all going together as sort of things that have to do with a common customer. And that might not seem super useful, but imagine if I want to make predictions about whether or not someone is going to default on a loan. What I want to do is get a bunch of past vectors that show people who have gotten loans from us and who did default, people who got loans from us and who didn't default. And what I want to do is somehow compare those vectors to this person who's applying right now and say essentially something like, which vector are they closest to? Are they closest to one who did default or one who didn't default? And maybe I'm going to make my decision about whether to give them a loan that way. But the bottom line is, each one of the customers that has been, gotten a loan from us or has been rejected from a loan from us has some set of data that all goes together, so it totally makes sense to treat that as a vector. All right? Here's some other examples. Think of like an audio file, like an MP3 or something like this, right? This is another time series-y thing. Might surprise you that that is a mathematical object, but it certainly is. And when you listen to, Led Zeppelin or Lady Gaga or whatever you listen to, right, you may have seen a picture at some point that looked like this. And this is a picture of the waveform of the MP3 file. And you might wonder what this is. And really what this is a measure of, this is time. And this here, on this axis, is air displacement. Now, what the heck does that mean? Well, when you have a speaker system or even headphones that you're listening to, the way that we hear sound is, as you may know, the air vibrates, right? Which is why you can't hear sound in space, Star Wars notwithstanding. If you're out in space, there isn't any way to hear any sound at all because there isn't any air to vibrate, right? But when we're on Earth or other places, the air vibrates, and the way you hear a song, or you hear my voice right now, is that the vibrations of the air are moving in a particular way that makes me sound like I'm making certain vowels and consonants that you can understand, or that makes Jimmy Page's guitar solo sound the way it does. And if you look at a song, it's essentially what is the air displacement over time doing? And the speaker or the headphones is going to push the air back and forth, I kid you not, in exactly that pattern. So when you have like an MP3 file, essentially what that is a record of, as the song goes through from second to minute, exactly how far in and out is the air going to be going, so that when I listen to that air displacement, I hear the song. So if you think about it, that is also a perfect example of a vector, right? Because what we can do is take at various points in time, and by the way, this is called sampling, and we're going to have a certain sampling frequency, which basically means every however many milliseconds do we want to measure how far the air has been displaced. And if we do that, we're going to get one big honkin' long vector where it's 0, and then it's 1, and then it's 2, and then it's 1, and then it's 0, and then it's -1, and then it's -2, and then it's -0.5, and then it's 0.5, no, right? And over here it's all the way up to 5, and over here it's all the way up to 8, and over here it's all the way down to -10, right? But if I keep track of what is the y value for every x value here, I'm going to get this big honkin' long vector that says 1, and then 2, and then 1, and then 0, and then -1, or -1.5, and 2, etc., 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 etc. And that, my friends, essentially is an MP3 file. Now, of course, I'm simplifying here, and there's a lot of things that MP3 format does to compress things and make it so that you can have a song that sounds good without taking as much space. There's a lot of details I'm glossing over. It's also in stereo, which means there's actually 2 different channels doing that, right? So I get the left ear and right ear being different. But essentially, that whole thing is a time series vector. And maybe I want to do something like find the places in this vector where there are gaps. Maybe it's something I recorded where it was live at a concert, and they played a song, and then there was a gap, and then they played another song, and there was another gap, and maybe I want to analyze that thing and say I want to put markers there so I can make each one a different CD track so I can quickly zip back and forth, right? That is a vector operation where you basically say, take this big vector and find the places where there's enough zeros in a row to call that a break. Find the places where there are breaks between songs. Or maybe there's a certain phrase I'm listening to. There was a big, long solo that Eddie Van Halen played, and there was this one part that was really cool, and I want to say, hey, computer, can you search through the MP3 file and find me the place that best matches this little 2-second clip, so I can say, yeah, that's when he started doing the thing, and I can zoom in and listen to that part right there, right? That's another vector operation. Again, the whole idea is we're treating this entire sequence of numbers as one composite mathematical object that we can then perform operations on, like finding the needle in the haystack type thing, right? All right, good. Let's do another multimedia thing here. So image files can also be represented in binary, and you may know that everything in a computer has to be represented in binary. So imagine if we have something like, a JPEG or a GIF or a PNG or something like that, right? And maybe it looks like this, and, it's this nice little mountain scene here with red mountains, I guess, and a sun, and blue rays coming out of the sun, and then we've got some grass here, right? Okay, so there's a picture here. You've seen lots of these in your life. Now, the way this is represented in a computer, you may know, is it's divided up into things called pixels. So imagine if I took this thing and carved it up into this gigantic tic-tac-toe board thing. Each one of these little pieces is called a pixel. And basically, the way that you can represent an image in a vector format is to basically say, let's represent each pixel as an element in a big, long vector. Now, if it's a black and white picture, you can imagine that each pixel has a certain intensity. Maybe I say that 0 is completely black, and 1 is completely white, and everything in between here, like 0.5 is midland gray and 0.1 is really, really dark gray, right? So basically I'm establishing a continuum here, and I'm saying that the closer each pixel's number is to 0, the darker it is, and the closer to 1, it's whiter. And if I just list all these pixel values in a row, all the way across the first row, and then all the way across the second row, and then all the way across the third row, etc., 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 I can basically make one big honkin' long vector that says 0.5, 0.5, 0.4, 0.3, 1, 1, 1, 0.9, 0.8, dot, 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 dot. And that whole thing is an image file. And you may or may not have heard that if you represent things in color, fun fact, you can represent any color that the human eye can see in 3 components: red, blue, and green. These are the primary colors of light. You may object that there's not yellow here because you may have learned that red, yellow, and blue are the primary colors. It turns out those are the primary colors for pigments, not for light. These are the 3 primary colors for light. Anyway, all you have to do to represent a color image is 3 different vectors. You might say we have a vector that is the red vector, and a vector that is the blue vector, and a vector that is the green vector. And basically, each element in each of these different vectors gives the intensity of that color that that pixel has. So right here on the sun, let's say this is just, super, super bright red and nothing else here. Well, that pixel, wherever it occurs in the sequence, let's say, somewhere down here, dot, 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 we have this pixel that goes with right in the middle of the sun. That is going to be 1 here, and it's going to be 0 in the blue vector and 0 in the green vector, because that pixel was all blue, all red. Whereas right here, maybe this is kind of, mostly blue, but also a little bit of red in the sky, and maybe a little bit of green. So that color right there, wherever that pixel occurs, is going to maybe have a 0.1 in the red, and it's going to have a 0.9 in the blue, and maybe a 0.3 in the green, right? So if you have 3 different long vectors like that, that's a way of representing what the image is in terms of a mathematical object. And now you can imagine doing all kinds of interesting things with that vector. Like, I want to find the faces in that image, right? That's something that your iPhone can do or whatever when it zooms in to focus or does some of those weird things where you make your face do kind of weird things with the different effects that you can kind of play around with. That's basically, believe it or not, a linear algebra operation where it says, I've got this huge vector of a bunch of pixels. Where are the faces? How can I define what a face is likely to look like in terms of the pattern of the pixels so that I can actually find that thing, right? Or you could say, let me take an image and let me compress it in some ways. Maybe there's a bunch of pixels in a row that are all the same shade of blue, and I don't need to repeat those pixels a million times. I can just basically make a record of, hey, there's 150 in a row that all have the same color here. That's called run length encoding, and you can basically reduce the amount of kilobytes that the picture is required to consume on your hard drive, or that you're sucking over the internet in terms of how much bandwidth you need because of how many bytes you're going to take over the internet, by basically finding areas of the picture that can be compressed. All those things are linear algebra operations operating on those images as vectors. Okay? Another example here, anything that involves a binary string. I think I've lost track of what number we're at, but we're on some number here. A binary string, right? Let's say I'm sending a message to somebody, I love you, Francis. I'm going to write some email or some text or whatever to them like that. This thing right here can be broken down into bits using a code called the ASCII code. And the way that works basically is every single letter or space or punctuation mark or whatever has a certain code, and that code, fun fact, is 7 bits long. So capital I don't know what that is. Let's pretend it's 1001000. And let's pretend that a space is 01000000. And let's say that a lowercase l is 11010111, etc., 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 right? We're effectively defining a vector, aren't we? And we could represent this entire vector as a sequence of ones and zeros, where each one is indexed with a certain value here. Now, suppose I want to send this thing encrypted, because maybe I'm embarrassed that I love Francis and I don't want anyone to intercept that message and be able to read it. We could represent our key. A key is essentially the way that you can encrypt something using most cryptography schemes. I'm going to have a key that is 10100000010111011. It's basically a big, long string of bits that is unique to me. And it turns out that there's a linear algebra operation whereby I can take my message, I can combine it with my key, and I can come up with an encrypted version of the message. So up here, this is called the plain text. And this down here is called the ciphertext. And now this thing right here, I can freely send over the internet, and anybody who read that would have no idea what my original message was, because there is essentially no way to get the original message back from the ciphertext unless you have the key, in which case you can reverse engineer what the plain text is by reversing that process. And all of those things are linear algebra operations operating with these things as vectors, as we will see. Now, here's one that may completely blow your mind that this would be a vector thing at all, but I assure you it is. Let's say we're talking about something like a Google search, where I want to say, hey, I want to go to Google, and I want to go to my search box, and I want to type in, oh man, Star Wars Episode 7, man. I want to learn some reviews for that thing to see if it was a good movie or whatever, right? You may wonder how Google does that. It's pretty amazing how it is able to find your needles in a haystack that has billions and billions of billions and billions of pages in it, and to do so super fast. What it does, I kid you not, and this of course is a simplified view, like everything I'm doing in this segment is, but this is very close to being the truth. What Google does is it does something called the vector representation of a web page. Now, what is the vector representation of a web page, you might ask? It's essentially this. Imagine a big, big honkin' long vector, and instead of using numbers to index them, I'm going to use words. So I'm going to use the word aardvark, and then the word abate, and the next element of my vector is going to be named abscond, and the next one is going to be named add, and then and then all the words in the English alphabet, all the way up to zoology, which is the last one. So say I have every word in the English language, and really we're going to say any sequence of characters that appears in a web page, but just let's leave it as English words for now, which there are like 50,000 words or something like that, right? So imagine this vector being 50,000 words long. Now, what I'm going to do is something that seems like it would not work at all, but I assure you it unbelievably works, and that is the so-called bag of words model. And what that does is it says, let's just treat a web page as a big bag of words, which basically means I don't care what order the words occur in on the web page. If I go to some web page here, and it says, welcome to Amazon.com. Buy our products now. Let's say that was the entire web page. Well, what we're going to do with this bag of words model is we're going to say, let's just take all the words in the web page and essentially throw them in a bag and shuffle them up. And then it doesn't really matter that welcome was the first word, or that now was the last word, or that to came immediately after welcome. We're just going to say, you know what, let's just keep track of how many of each word there was. So maybe on this particular web page, it had the word aardvark not at all, and it had the word the word abate 0 times, and the word abscond 0 times, and maybe down here it has the word Amazon once, and somewhere it has the word com once, and it also has the word, somewhere in here was the word buy, and it had that once. And maybe if I make this longer, it ends up having the word and 5 times, and the word add once, because it says add to your shopping cart, and maybe it has the word to 4 times, right? So we're basically making a vector that simply is a bunch of word counts. How many different times does each word in the English language appear? By the way, this is going to be something that is known as a sparse vector. And the reason it's sparse is because if you think about it, for any web page that's worth its salt, the vast majority of these entries are going to be 0, right? There's a heck of a lot more words that don't appear than do appear. And it turns out that if it's a sparse vector, we can represent this more efficiently. But would you believe that the way Google finds pages is it basically says, let me take the words you typed, and basically it does an algorithm which says, let's find pages that simply have the words that you typed up here a lot of times. And maybe we could say, you know what, I'm going to return a certain web page as the first one in my hit list because it had the word episode 3 times, which is really disproportional. Because almost every page has the word and a lot, and a lot of pages have the word to a lot, but not many pages have the word episode a lot. And since you had that 3 times, and by the way, you also had the word star 10 times and the word wars 10 times, I mean, my goodness, those are extremely disproportionate. And therefore, it figures that's a page you might have been looking at. This same technique can be used for any kind of text. Imagine if I had some email, and I said, here comes a email message, and it says, buy Viagra now, low prices. I could represent this thing as a vector that has the word aardvark 0 times, and has the word buy once, and has the word low twice, and has the word now once, and has the word Viagra once, etc., etc. I could represent this whole thing as a vector, and then I could say, hey, you know what? All the emails I've seen before, each of which have their own representation as a vector, which one is it more like? Is it more like, or excuse me, is this one more like the ones that have been marked spam? Or is it more like the ones that are marked non-spam, which is also sometimes called ham? And by saying, if it's similar or more similar to the spam ones versus the non-spam ones, we're going to mark that email as spam. And that is basically how spam filters work. So something that doesn't seem like it has anything to do with numbers or math at all turns out to be precisely a linear algebra concept, simply because we can take the elements that are in it and we can do a count of how many words there are, and then we can treat that thing as something that can be similar on some measure to other vectors more than others, and do sort of a classification that way. Fascinating stuff. Imagine if you are on matchmaker.com or some site like that where it's trying to connect you with potential dating partners, right? Well, they could give you a survey, and they could say, answer to survey, how much do you like action movies on a scale of 1 to 10? Oh, I like them a 7. How well do you like romantic dinners on a scale of 1 to 10? Oh, I like those 2. I don't really like going out for dinner. I like to stay in. What do you like in terms of books? Do you like to read certain kinds of books? Oh, I got a 3 on that, right? So imagine if somebody goes to matchmaker.com and pays to be on the site, and then does this kind of survey type thing, right? And this is their vector. Maybe this is the vector for Dave. And then also on the site is Julia, and also Beverly, and each of them has a vector, and we'll say that Julia can't stand action movies, Julia loves romantic dinners, and Julia is an avid reader. And then let's say Bev is kind of iffy about action movies. She can take them or leave them. She knows she likes to stay in for dinners, though, not to have dinners out, so that's a 0. And she doesn't really like books that much either. Maybe she's a 3 there, etc. What Matchmaker.com basically does is it does a huge amount of computations on vectors of this kind to say, hey, who should I recommend that Dave hook up with? Should I recommend him Julia? Should I recommend him Beverly? Should I recommend him something else? And just looking at this, you can tell that Julia is going to be a worse match for Dave than Bev is. And that's because Dave and Bev have more similar values here for these different things. And there is a way to quantify that, which we'll learn, that basically says, hey, of all the different vectors in Matchmaker.com, give me the top 10 that are most similar to Dave so that we can represent, or recommend, rather, who he might be able to date, right? So same kind of mathematical thing, finding which vectors are similar to which other vectors, even though it started with a very different thing. It started with dating partners and personalities instead of starting with email messages and text, but it boils down to the same thing. And once we are able to leverage it in terms of a linear algebra representation, we're able to bring all of the things we're going to learn in this class to bear on it, and we're going to be able to number crunch this thing and figure out how to do a lot of cool stuff, right? All right, a couple more things here. While we're on the topic of social gatherings or social networks, this is something that comes up in my research that I'm working on a lot now, is social networks. So imagine, you're dealing with something like Facebook, right? And if you've taken volume 1 of all the math, you'll remember that there's a thing called a graph. And a graph is essentially a bunch of vertices that are connected via edges to different other vertices. So let's draw a few here. And we'll say that each one of these represents a user on Facebook. That's Dave, and this is Filbert, and this is Beyonce, and this is Kanye, and this is Kim, and this is Finn, and this is Ray. Okay, so these are all different people. And if there's an edge here, basically that means that those two people are friends, right? So Dave and Kim are Facebook friends, and Dave and Finn are Facebook friends. But according to this graph, Dave and Kanye are not Facebook friends because they don't have an edge between them, right? So I could represent Dave here as a vector, and that vector is going to be the vector 1, 1, 0, 1, 1, 0, where this one is labeled as Finn, and this one is labeled as Kim, and this one is labeled as Kanye, and this one is labeled as Ray, and this one is labeled as Beyonce. I guess this should be a 1, because this is Filbert's here, and we are friends with Filbert. Right? So you see what's going on here. We've basically got a 0 for every one that we're not friends with, and we've got a 1 for every one that we are friends with. So we have reduced Dave in terms of the Facebook social network to a vector of 1s and 0s. And now we can do a lot of really interesting things, like saying, hey, in this little subgraph of Facebook, who are the most influential nodes? If I wanted to sow a rumor about two people dating or breaking up or something like that, who would I give that rumor to make sure it spreads to the maximum number of people? Or what if I wanted to make sure so-and-so didn't hear it? Who would be the best person to spread that rumor to so it would spread to the most people, but not include so-and-so who I think might be pissed off from that rumor, right? All those things are possible once we have this thing reduced to a bunch of vectors, because we can do vector operations that reduces those kinds of questions, believe it or not, about who's the most influential, who's the most connected person, down to a math problem. All right? 2 more examples. How does Amazon figure out what products to recommend to you, or for that matter, Netflix, which movies are you going to like, or anything like that, right? The way it does it is it has a purchasing patterns vector, where it says, hey, Julie, what has she bought lately? Did she buy product number 1, which is a waffle iron for us? No. Has she bought a weightlifting set from us? No. Has she bought a crochet hook from us? Yeah, it turns out she's bought 13 of those. Has she bought a Harry Potter book from us? Yeah, she bought 2 of those, etc., right? So again, we have represented Julie as a vector here. And we can ask questions now like, what product should we put on Julie's landing page when she comes to Amazon.com? And that's going to come down to, well, you know what? She brought crochet hooks. And a lot of other people who bought crochet hooks also bought weightlifting sets. Because we all know that people who crochet tend to be people who lift weights. I mean, not always, but those tend to go together. So if there's a lot of different vectors that have some positive numbers here and some positive numbers here, then weightlifting turns out to be a great product to represent or to recommend to Julie, because she has liked things that those other people who have bought weightlifting sets like. And that's exactly how Netflix figures out what movies to recommend to you, right? It says, hey, other people who liked The Walking Dead and Daredevil and Orange is the New Black also liked Mad Men. Therefore, we're going to recommend Mad Men to you. But we're not going to recommend Battlestar Galactica to you, because it turns out that most of the people who like those other movies that you like don't like these, right? That turns out to be a huge linear algebra math problem to figure out what are the optimum best movies to recommend to you based on which ones you like and which ones other people who like the ones you like. Fascinating stuff. Last one. A lot of times we're going to use these vectors to represent the state of a system. So one way this comes into play is something like population growth. So we might say, right now there's some colony on Mars or whatever, and I'm going to represent their current state vector, which it's called. We're going to call it pop, maybe, because this is the population vector. And you might say population, isn't that a scalar quantity? Isn't it just how many people are living on Mars? Maybe. But maybe we want to say how many different people of different ages are living there. So we might say that right now in our colony we have 12 people who are age less than 5. And we've got 111 people who are ages between 5 and so this is like, I don't know, age less than 5. This is age between 5 and 10 or something like that, right? And then we're going to say I've got 719 people who are from age. I guess this shouldn't have been equals, right? Between 10 and 15, right? And so basically what I've got is all of the demographic life stages and the counts that each one of them have, and that is a representation of the sort of age makeup of my colony right now. And then what I can do is I can run a simulation on this, maybe using something called a Markov chain, which we'll learn an application for later, that basically says each time a year goes by, some of those people in the under 5 category are going to move up to the 10 to 15 category, and some of the ones in the 10 to 15 category are going to move up to the 15 to 20 category. Some of the people in the 20 to 25 category are going to be pregnant and give birth to newborns, right? And so there's going to be a continual influx of young people as long as we have enough, child bearers in our population. And so what we can do once we have that vector and once we have the transition probabilities, we can say, let's project 100 years into the future. How many kids are going to be on this Mars colony? How many adults are going to be on this Mars colony? How many people who are elderly and need certain kinds of medical care because of that age group that they're in are going to be in our colony? What's the total population of our colony going to be? Is it going to go up and is it going to go down? That is all possible to do with vectors and all the different vector operations we learn once we've reduced it down to a representation that has to do with a vector, which is, again, simply a collection of quantities that are all like a sequence or that all have some label on them that allows us to keep track of it, right? So this is just a tiny, tiny smattering of the different operations, or the different applications rather. But the big point I want you to get out of this segment is simply that there's all kinds of stuff that you deal with and use every day that boils down to linear algebra operations. And once you are able to represent things as a vector, you have all the machinery that we can do complex things to bear, and you can do a lot of the great things that we are seeing in the technology world that we have today.